Hello and welcome to another adventure together. Let's say that we have these two objects, and when they collide, they follow this particular path. And it is predictable. We can solve it. Because even though energy may not be conserved in a collision, momentum is always conserved. And we can always solve these problems using one of three different techniques. Either with a scale diagram, by component method, or by trig method. Now, trig method is going to be the craziest, so that's why we avoid it. But we'll start off with the scale diagram first. All right. Now, many of us believe that with a scale diagram, you're only limited into drawing things that have to do with regards to distance, for example, measured in meters. But that's not always the case. As long as your diagram is a vector diagram, you can also measure it in, for example, velocity in meters per second, acceleration, force, or in our case over today, kilograms times meters per second, which is a measurement of momentum. Just keep in mind that in all scale diagrams, you need to include a coordinate system so the reader knows what you're defining as positive. First off, we'll take the vector that represents the momentum of the first object. So let's say this is momentum of object number 1. And then we're going to add it with the momentum of object number 2. And we'll connect them in the fashion of from head to tail, like so. This is our end result, and that is our total momentum. And as discussed, even though energy may not be conserved, momentum is definitely conserved. So momentum before is equal to, I'll color it differently, the momentum afterwards. All right, so we have vector number 1 for momentum 1 afterwards, which is this one here. And then we'll add it with, let me just draw this a bit longer. We're going to add it with momentum number 2 afterwards. And it should also share the same total momentum. And that's how you'd solve it using a scale diagram if you were to draw it more carefully than I did. And that's why things don't match up perfectly here. All right. You can also see that if you try solving this using the trig method, it's going to be a nightmare. Because in this case over here, when you're trying to solve for this vector, it's not a triangle anymore. Now it's a quadrilateral. So you need to break it down into a smaller triangle, solve for its resultant, and then solve for the second triangle. It takes a long time. So the easiest way of solving these problems is, as you may have guessed it, by component method. By component method, what you need to do is that you need to solve for momentum in the x dimension, then solve it in the y dimension, glue them together using, guess what? That's right, the Pythagorean theorem. And lastly, because this is a vector, you also need to include an angle. So don't forget about this part as well. All right, and just so that there's some numbers and context to this, how about I give you a set of givens? All right, so here are the initial velocities of object 1 and 2. And let's say that I've only given you the velocity of object number 1 after the collision. And the question is, what is the velocity of object number 2 after the collision? Give you a moment to solve it. You can play this video afterwards. Ready for the answer? Here we go. Did you get it? If you did, good for you. You can fast forward to the videos in the next chapter. And if you want to see me go through this, then yeah, let's take the time in solving this question together. So when we solve it together, I'll just leave this as the blown up version so we can carefully see what's going on. We're going to take each of these objects and their corresponding vectors and break them down into their vertical and horizontal components. By drawing out these vectors, it just helps us figure out when to use sine and when to use cosine. At home for the answer key, let's answer this the long way. All right, we know that total momentum before the collision is equal to the total momentum after the collision, and we're going to deal with the x dimension first. Okay, so we're going to factor in this vector here, this vector in here, this one over here, and we're trying to solve for this one over here. Okay, so we know that momentum is equal to mass times velocity, so m1 v1 plus m2 v2 is equal to, or in the x dimension, is equal to m1 v1 apostrophe in the x dimension plus m2 v2 apostrophe in the x dimension. Now, the x dimension for here, you'll notice it's opposite of 30 degrees, so that's why we're going to use m1v1 times the sine of 30 degrees. Oh, this vector over here is pointing to the left, so that's why we need to subtract, all right? Because if we assume right is positive, then left needs to be negative. So minus m2 v2 times the sine of 45 degrees is equal to m1 v1 times the sine of 10 degrees. And I don't really know which way this vector will face. I mean, in our animation it pointed to the right, but I didn't know. All right, so I'll just assume that it's going to move to the right, and if we get a negative answer, then we know that it's going to move to the left. So this is m2 v2 apostrophe. You could type in sine of theta, but since we don't know what theta is yet, we'll just keep it as v2x. In fact, this is what we're trying to solve for. Okay, so we're going to isolate for that next. So v2x is equal to m1 v1 times the sine of 30 degrees minus m2 v2 times the sine of 45 degrees. When we bring this term over, that will be a negative term. So minus m1 v1 times the sine of 10 degrees. All right. Sometimes I do swap-roonies in my head. So since I know that all the terms on the right are going to go to the left, then I just envision this already being on the right-hand side. Okay, and that's why the term over here becomes negative when you bring it over to its correct side. Okay, we're going to divide everything by m2. Now, if you didn't divide everything by m2 and you left it over here as an m2 v2x, then technically you've solved for your momentum in the x dimension. All right, and if that's what you're trying to solve for, that's perfectly fine. But in this question here, since we're cutting to the chase and we're trying to figure out the velocity of the object at the end, we'll divide by the mass right now just to get that over with. We then sub all the values in, so m1 is the first mass. It's traveling at 3 meters per second times the sine of 30 degrees because we want the horizontal component. The second object is not moving to the right, it's moving to the left, and that's why there's a minus sign. And so it's 2.0 meters per second. Whoops. What's the mass? 1 kilogram. 1 kilogram times 2.0 meters per second times the sine of 45 degrees. And after the collision, remember, even though it was moving to the right, we use a minus sign because we rearranged the equation. Okay, so subtract the first object's mass, 4 kilograms, and it's moving a bit slower now. Now it's down to 2 meters per second, but we do know the horizontal component, which is the sine of 10 degrees. We divide all of this by the mass of object number 2, and through the magic of PowerPoint, here's the answer. And we're going to rinse and repeat in the y dimension as well. Okay, so in the y dimension, we're going to add this vector here, which is m1 v1 times the cosine of 30 degrees, plus this vector over here, which is m2 v2 times the cosine of 45 degrees. And that's going to be equal to m1 v1 times the cosine of 10, well, apostrophe times cosine of 10. And we're going to assume that the object does travel upward still after the collision. Depending upon how they collide, I mean, in this case over here, we saw that they collided in this fashion, all right, where they made contact right here if you rewind back. There is a possibility where if the ball was down here and it collided, well, then it may cause it to ricochet and bounce downwards. That is a possibility. There's also the third possibility where they completely miss each other and they just continue on their own merry path. All right, that possibility does exist. But that's why we need to have at least one answer of the outcome afterwards. So in other words, we need to find out either what object number one's velocity is after the collision, or what the second object's velocity is after collision, or if you're a bit more hardcore, the angle between the two after the collision. You could solve it using, you can solve any of these cases, right? So you need to know at least something about the collision afterwards. Okay, so this is m2 v2 in the y dimension apostrophe, and that's what we're trying to isolate for. Okay, our v2 in the y dimension after the collision. So that's equal to, and I'm going to sub everything in now, m1 is our 4 kilograms times the velocity of 3.0 meters per second times the cosine of 30 degrees minus object number 2, its speed. Did I get that right? No, 2.0 meters per second times the cosine of 45 degrees, and subtract object number 1 now after the collision's new velocity and new corresponding direction, and divide all of this by mass number 2 of 1.0 kilograms. Once again, through the magic of PowerPoint, that would work out to this answer over here. To finish things off, we need to find out what our v2 apostrophe's velocity is, or the magnitude of it, which is equal to v2 x apostrophe plus v2 y apostrophe. I'll put it in brackets because it should be squared when you use the Pythagorean theorem. .928 meters per second squared, and once you pull out your calculator, you get an answer of, I believe, 5.1 meters per second. Is that it? Yeah, 5.1 meters per second. And then when you do the tan inverse, and when you do the tan inverse, there's two ways of doing it, right? You can either do it with the opposite, or the vertical component versus the horizontal, or the horizontal versus the vertical. It's up to you how you decide to draw it. Now, I'm going to draw it in such a way that I'm going to start off with a 3.197, positive, meaning it moves to the right, and then we have the 3.928 as the vertical. And seeing that the vertical is longer than the horizontal, we know that this theta over here should be greater than 45 degrees when we calculate it out. Okay, so we're going to do the tan inverse of our v2y over our v2x. So that's equal to the tan inverse of v2y, which is 3.928 meters per second, divided by 3.197 meters per second. And if all goes well, what happened? Oh, yeah, that's 39 degrees, so my answer would be different. It would be, yeah, 51 degrees. Okay, so if I did it y over x, then I'm going to have an answer of 5.1 meters per second from the right, 51 degrees upwards. Or the answer key had it the other way around, upwards relative to the right. They're both correct. All right, either way you do it. Now I see there's a bunch of other scribbles in my PowerPoint. One thing about this weird collision here is that you'll see that the energy afterwards still happens to be a bit more. And if you're wondering how do we calculate total energy, well, it's not too difficult. Total energy is equal to 1/2 mv1 squared plus 1/2 mv2 squared. Okay, that's the total energy you had before the collision. And after the collision, well, you're just doing the same thing again, but this time around it's the prime versions, right? So mv1 prime squared plus 1/2 mv2 prime squared. And if you need to put in brackets, just so you don't accidentally write down 12, then by all means include the brackets. And that's how you find out the total energy before and after the collision. In general, energy is lost due to it being converted normally into heat or sound. If it ever does increase slightly higher, it's one of two things: either A, the problem's impossible and you made a mistake, or B, there's explosives. All right, so if the two collide with each other and one of them is carrying some explosives, then yes, it will definitely add more energy to the system. That can happen. As I mentioned, this can be solved using trig method, but it just takes way too long. All right, so stick with component method, and if you need to draw a scale diagram just to make sure that you're in the correct ballpark answer, by all means, go and do that. Alright, for the remaining of this video, just follow along with me visually. There isn't really anything to copy down. But this one's a more interesting one. Alright, whenever you toss an object into the air, for example, the squash racket, its path may seem rather erratic. Alright, things are just wobbling around everywhere. But that's because you're looking at the object as an entire. What you should be really focusing on is where the center of mass is. All right, so if you find out where the center of the mass of where the squash racket is, denoted by that highlighted orange dot, you'll notice that the path and trajectory that it makes is a perfect parabola. And now they're going to pick up other objects and toss them around. And you'll notice that in all these examples, the center of mass maintains a perfect parabolic path. That's a better version. In all given objects, whether it's being influenced by the impulse of gravity or two objects are colliding with each other, its center of mass will always be maintained. I like showing videos because videos can show you, everything that's happening in real time as opposed to textbooks. So, here's an image that you can find in a typical textbook about collisions, and you're supposed to read it from top to bottom. So this is showing you, a red ball and a green ball before the collision and their corresponding directions after the collision. All right. And these are just pictures that are taken, once or 10 times per second, once every 10th of a second. And you can see that object number 1 is moving rather slowly, and object 2 is moving rather quickly. And then afterwards, object number 2 moves very slowly, and object number 1 seems to speed up a bit. All right. So if you just look at just the red object and the green object alone without looking at anything else, there doesn't seem to be any sort of discernible pattern. But this time around, let's focus on its center of mass. So in other words, this dot over here represents the center of mass right over here. This dot over here represents the center of mass right over here, and so on and so forth. So this time around, when you pay attention to it from that perspective, you'll notice that the center of mass maintains its same path after the collision. All right, so that's the point of this, and this is probably the only thing for you to copy down. In any collision, the center of mass always retains its momentum. And if you haven't gotten these last 3 points down yet, then please do so. All right, there are 3 different types of collisions that may exist. The first kind is one where energy is conserved, and that's known as a perfectly elastic collision. So total kinetic energy at the beginning is equal to the total kinetic energy at the end. There are times where some of the energy is lost, and it's just simply denoted as an inelastic collision. And yes, the third one, there is such thing as a perfectly inelastic collision, and that's where the two objects fuse together, and when they bind together, they share the same velocity afterwards. All right, maybe copy that down earlier, and if you didn't, well, now's your chance to jot it down again. In any case, that's all for today. Here's the homework, and once you've done the homework, please read ahead because we have a lab coming up right up next. See you in the next episode.